What's up, bitches? Today we're going to learn the refrigeration cycle. So let's get right into it. It starts with a compressor. Okay, step one. After, it goes into a condenser. After that, it goes into an expansion valve. And after that, into an evaporator to return back to step one. That's it. That's a refrigeration cycle. It's super easy. But you don't, for your exam, you don't need to know any of this by heart. Okay, this is just like details basically. What you need to know is the TS diagram. All you need is a TS diagram to answer all of your questions. So I'm just gonna draw that real quick and explain everything. Okay. For this cycle, you need the saturation lines over here. Okay. Basically, what it's saying over here is whatever is on this line over here, on this half, is a saturated gas. Whatever is on this line over here is saturated fluid or liquid. I'm just going to write L. Okay. Whatever is out over here, outside of these lines or outside of this curve, it's basically superheated refrigerant. That's it. So step one usually is going to start on this line over here as a saturated gas. Then it's going to go straight up. Okay. S1 and S2 is going to be the same. Then back down over here as a saturated liquid at step 3. Then at step 4, it's going to be like somewhere around here. And it's going to maintain the same temperature, but it's just going to increase the entropy. That's it. That's the refrigeration cycle. For this cycle, you're going to have heat coming in over here, Q in, and heat exiting over here, Q out. Work is going to be done onto your system from point 1 to point 2. Another thing you have to keep in mind, from point 2 and 3, it's constant pressure. I'm just going to write CP. From 4 and 1, it's also constant pressure. Point 3 to 4, you're going to have constant enthalpy, constant H. H. And that's it. This is the entire TS diagram for your refrigeration cycle. If you're allowed to have a crib sheet, you should copy down exactly this TS diagram, okay? So, for this chapter, they're going to ask you some questions. They're going to ask you for the COP. This is the coefficient of performance, which is just a fancy way of saying, oh, how efficient is the refrigeration, okay? The COP is going to be equal to the heat that comes in divided by the work being done on your system, okay? Some questions is going to ask you for the reversible coefficients of performance. Damn, hold on. Right, okay? That's going to be equal to TL over TH negative TL. Now, what the fuck does this mean? Coefficient of performance of a reversible cycle is basically measuring the best case scenario efficiency of your refrigeration, okay? In thermodynamics, a reversible cycle means that it's like theoretically the perfect cycle. No friction, no enthalpy change, nothing, okay? So whenever they're asking you for the COP reversible, they're asking you to measure the problem states that there's 2 reservoirs, and it's going to ask you to measure like how efficient the system is for these 2 reservoirs. TL is the temperature of the reservoir with the lower temperature, and TH is the hotter reservoir, okay? Now, if it's a heat pump, first of all, it's going to state in your problem statement that, oh, it's going to be a heat pump. Basically, it's the exact same cycle, like it's the same TS diagram. It's just the purpose for it is different. It's the heat pump is meant to send heat in a space, and a normal refrigeration cycle is just it's meant to send cold air into a space. If it's a heat pump, your equations changes. The COP becomes Q out divided by W in, because that's the whole purpose of the system. COP rev is equal to the hotter reservoir divided by TH negative TL. You don't need to know all of these by heart. You just really need to understand the purpose of these two systems. And the rest is kind of easy to understand. Okay, one last thing. Unlike the Brayton cycle, we're not going to measure the work done or the Q with Cp delta T. Here, you're supposed to have the tables for your refrigeration. For my final exam, my professor just gave us the values for the H's, but you have to check with the pressure and temperature, and sometimes also the entropy. You're supposed to find the enthalpies, the H's. So every work done or heat Q in or Q out is basically the difference of the enthalpies. So for example, from 0.4 to 1, Q in, here it's from 0.4 to 0.1. So it's going to be equal to H1 negative H4. If in your exam, you do H4 negative H1 by accident, you're going to get a negative value, okay? You're not supposed to have a negative value. So if that happens, it just means that you messed up the signs. It's supposed to be this, for example. And that's it. So if you want to know by heart anything, you have to know by heart this TS diagram. So now let's move on into an example. All right, guys, we're going to do this problem. I'm going to try and keep it as simple as possible because this problem is low-key. It's not hard, but it's just complicated, okay? It's asking for the quality at the evaporator inlet. That's 0.4. The refrigeration load, which is just a fancy way of saying M dot, COP. And the maximum load, which it has something to do with the reversible shit, COP. Okay? So, the first thing that you want to do is you want to draw the TS diagram. Okay? This is going to help you to not lose track, and it's also going to give you partial credits in your final exam. 0.3, 4. Okay, what's very important is you draw these lines so you don't lose track. Q in, Q out. And over here, 0.2 to 3, it's constant pressure, constant pressure. Here it's constant H, okay? So, let's start the problem. 2 T4 T4. Here it's saying that where is it? The refrigerant enters the condenser. That's the condenser is at 0.2 at these conditions over here. So 1.2 MPa and 65 degrees Celsius. Keep in mind that 0.2 and 0.3, it's constant pressure. So here's going to be the same. And leaves at 42 degrees Celsius. The compressor inlet, that's 0.1, has 60 kPa. 0.1 and 0.2 is constant pressure. So over here is also 60 kPa. At negative 34 degrees Celsius. All right. So also 0.1 to 0.4, it's just a horizontal line. Okay. What the fuck? It's a straight line. So T1 is equal to T4. 42 degrees Celsius. No, sorry. Hold on. Negative 34. My bad. Negative 34 degrees Celsius. All right. So let's start. Basically, to find all of these answers, you have to find the enthalpies. That's H1, 2, 3, 4. Okay. How do you do that? Well, let's start with 0.1. Okay. You go to 60 kPa in your tables for the refrigeration. And here we're going to realize that our temperature is higher than the saturated temperature. That means that it's superheated. Okay. So it's not going to be 0.1 is not going to be on this line over here. It's going to be more over here. Slightly higher. Whoops. And it's going to be a straight line. Okay. So you go to 60 kPa. So 0.06 MPa. And you have to do interpolation between the H and the T's. Okay. So interpolation, this is the equation. Plus the slope times x negative x1. Basically, we're trying to find H, okay? So, it's this value, 8, plus the slope, 78 negative 227.8 divided by negative 20, negative 36.95 times negative 34, negative 36.95. This is going to give us H1, which is about 230.06. Okay. Whoops. Oh, man. 230.06. Okay. You're going to do the exact same thing for 0.2. I'm just going to skip it, but it's the same principle. Okay. You interpolate it, you're going to get 295.15. Now for 0.3, when we check our tables, we're going to realize that our temperature is lower than the saturated temperature. When this happens, you go to the temperature you have, which in this case for us it's 42, and you just take the enthalpy, the saturated enthalpy at H3, HF, sorry. Which in this case, if we read our table, it's going to be 111.28. Now, why do we do this? It's just a way to estimate the enthalpy because it's accurate enough. When it's subcooled, the pressure doesn't really affect your liquid. So you can just take the saturated enthalpy as fluid, okay? Keep in mind that this half is liquid and this other half is gas, okay? Now for 0.4, we know that 0.3 and 0.4, it's constant H. So we're just going to write H4 is equal to H3, 0.28. All right. Now we have all of our enthalpies. We're ready to find, to answer the questions. So X4, quality is equal to H negative HF divided by Hg negative HF. This is just an equation that you have to know by heart, basically. Okay. So we're going to go to our temperature. Normally you could go to your temperature, but because our 0.1, it's not saturated, it's like slightly above. So we can't assume the same temperature anymore. Can't assume this, which is fine. Instead, we're just going to take the pressure, which is 60 kPa, and you're going to check the H values over there, okay? So us, we have 111.28. You take negative HF, which is 3.837, divided by, this is HFG, which I'm just going to write it down, 96. We're going to get a quality of about 0.4797. What the fuck? This is our first answer. Next, we need to find m dot. Whenever it's asking you to find the mass flow rate, you have to either look for a wattage here or another mass flow rate, okay? When you have a mass flow rate over here, automatically just take this, okay? It's going to make your life so much more easier. Because in this specific problem, 450 is irrelevant for our m dot. Okay? So here, it's basically saying that at the condenser, there's water coming out. Water that absorbs heat. And 450 is saying that the compressor receives 450 watts. Okay? But that doesn't matter. For our m dot, we have to look at the condenser. What's happening at the condenser? Basically saying that water enters at 18 degrees Celsius and exit at 26 degrees Celsius. Now your question is saying that it's just saying water. So one way to estimate the enthalpy of the water is that you're just going to assume, well, in your exam, you have to write, oh, that I'm assuming this, but you're going to assume that your water is the saturated liquid. So that makes our life so much more easier. We just look at HF at 18 degrees Celsius of water. So it's a complete different table. And at 26 degrees Celsius, which is going to be 75.54 and 109.012. All right. So basically, this is your Q out in our system. It's going to be the same as the heat absorbed by the water, okay? That's all it's saying, okay? So our mass flow rate of the refrigerant times delta H is equal to the mass flow rate of our water, which is 0.25 kilograms per second, times delta H, which is 109.012 negative 75.54. Okay. So which H's are we taking? You go to your TS diagram right over here, 0.2 to 0.3. So you take H2, this, negative H3, this. All right. Zero 0.25, 109.012, negative 75.54, divided by H2, negative H3. So 295.18, negative 111.28. This is going to give us a mass flow rate of about 0.0456 kilograms per second. That's it. Whoops. Next, it's asking the COP. Since this is not a heat pump, it's equal to Q in divided by W in. Now, normally you would just do this, but because there's heat that's coming into our system, you can't directly just take M times H1 negative H4, okay? Because this over here, it's not taking into H1 is not taking into account the heat that is coming in, okay? So whenever you have a problem like this, you just find the heat that's coming out where this does not affect it, okay? So we don't know the actual H1. So what you have to do is, first of all, we already have our Q out, which is equal to 0.0456 times 295.18 negative 111.28. Calculating this, you're going to get a value of about 8.38 kilowatt. Next, Wn is equal to m dot delta H. Which H's are we taking? You scroll up again, and it's over here, point H1 to H2. But you have to take into account this heat that's coming in, okay? The 450 watts. So H1 is equal to 230.0. No, sorry, you're taking H2 negative H1. My bad. 295.15 negative 230.06. Negative the 450 watt, but this is in kilowatts, so 0.45. This is going to give you a value of about 2.518 kilowatts. To find Q in, you have to take into account that the work being done is equal to Q out negative Q in. Okay, so our Q in is equal to Q out negative W in. This is just basic algebra. 8.38 negative 2.518. That's going to give you a value of about 5.8662 kilowatt. All right. Finally, you find the COP, Q in divided by W in, equal to 5.862 divided by 2.518, giving us a COP of about 2.32. That's it. Now, again, we can't just take 0.1 because 0.1 doesn't take into account this heat that's coming in, okay? That's why you can't calculate Q in directly from here, from this side over here. It's fine for the work being done because you're subtracting 250, but over here it's not that simple. So we're just going to calculate it indirectly using the other formula. It's much easier. Finally, to find the maximum load, you have to find the COP of the reversible cycle, okay? Now, as I said before, COP, rev, is equal to TL divided by TH negative TL. Where do we find these values? You go back to your question, and it's saying over here, it wants to keep a refrigerated space at negative 30 degrees Celsius. This is our TL. Our T high is over here, where the water comes in. That's what we're assuming. So, We take negative 30, but we have to do this in Kelvin. This is, sorry, 273 plus 18 degrees from the water. Negative 30 plus 273. That's going to give us a value of about 5.0625. This is the maximum coefficient of performance that we can receive. And keep in mind that COP is equal to Q in divided by W in. So for in this case, Q in max is equal to the work being done on the system times the maximum COP. Right. Okay. Which is going to be equal to 5.0625 times the work being done, 2.518, giving us a maximum refrigeration load of 12.75 kilowatt. And that, ladies and gentlemen, is how you solve a refrigeration cycle for thermodynamics. Thank you for watching. Leave a like, subscribe.